In the previous video, we talked about the two models for the BJT transistor, the two models that we can use for the small signal, the AC signal. One of them is called the pi model and the other one is the T model. And the important parameters in these models are the resistance R pi and GM, the transconductance GM, the resistance RE if you are going to use the T model. How to calculate these parameters? This is what we are going to discuss in this video. The resistance R pi, we said that you look at the relation between I base and VBE, the total I base and VBE, the curve, the exponential curve, and then you calculate the slope of this relation at the operating point. So R pi basically is the differentiation. R pi will be the differentiation between I base and dVBE. Okay, the total I base with respect to the total VBE at the Q point, at the operating point, and then this is the slope. You reverse the slope, you get the resistance. So basically it's the inverse of the slope. RE is the same, but from the IE curve. So you can get the slope from the IE curve with respect to VBE at the operating point, at the DC point, and then you take the inverse. GM can be calculated as the slope at the Q point of this curve, the relation between IC and VBE without inverse, because GM is the transconductance. So GM basically is the differentiation of IC with respect to VBE at the Q point. So in order to do that, we go back to the relations between I base VBE, IE VBE, IC VBE, which are these relations circled in the purple color. This is the relation between IC and VBE. The relation between IE and VBE, it's the same but divided by alpha. And this is between I base and VBE, same as IC but divided by beta. And these relations are between the total currents. Total means AC plus DC, and the total voltage VBE. So now, for example, if we want to calculate the let's try to calculate GM, for example. So we are going to use the relation between I base. So I'm going to remove and I'm going to write the relations once again. So the relation between I base and VBE is this relation. If I want to calculate GM, we will use the relation between IC. So IC equals IS exponential VBE over VT. So if we want to calculate GM, we are going to differentiate this relation. We are going to differentiate DIC with respect to dVBE at the DC point, at the Q point. So let's differentiate. If we differentiate this relation with respect to VBE, what we are going to get? We are going to get the same exponential divided by VT, right? At the Q point. At the Q point means at the DC operating point. But at the DC operating point, VBE, the total VBE equals what? At the DC operating point, the total VBE is equal to the DC value. So this will be equal to IS over VT exponential, and we replace the total VBE by the DC value of VBE. Why again? Because at the operating point, the total VBE, which is this axis, this is the total, at the DC operating point, it will be equal to the DC value of VBE, right? So this will give us what? This will give us the GM equals to, what is this? This is the DC value of IC. This is the DC value of IC. So it's the same IC when we replace VBE total by VBE DC. So it will give us the DC value of IC divided over VT. So this is how we calculate GM. We can do the same for R pi and RE. Let's do one of them and I will leave the other one for you. For example, R pi can be calculated as the differentiation of I base with respect to VBE at the DC point, and then we take the inverse. Okay? So this is I base with respect to VBE. So if you want to differentiate I base with respect to VBE at the Q point, we differentiate this relation. When you differentiate this relation, it will give us the same exponential Is over beta, exponential VBE over VT, and then this is divided over VT. At the Q point. At the Q point, what's the value of VBE at the Q point? This is the total VBE. What's the value of the total VBE at the Q point? The total VBE at the Q point, it is exactly equal to the DC value of VBE, right? So this is equal to Is over beta exponential the DC value of VBE over VT. All of this is divided by VT. Of course, we need to take the inverse, right? Don't forget, we need to take the inverse. What is this? This is the DC value of I base, right? So this is the DC value. Of course, we should take the inverse again. This is inverse. This is the DC value of I base divided over VT, and then we take the inverse. So from here it will be VT over the DC value of I base. So R pi will be VT over I base. Same thing, we can calculate RE, and we'll find that RE will be equal to VT over IE. So this is how we calculate GM, R pi, RE, and you will notice that their values, the values of GM, R pi, RE, they depend on the constant VT. This is the threshold voltage, which is usually 25 millivolt in room temperature. And it depends also on the DC values, on the bias point. On the bias point, the DC point of IC, the DC value of I base, the DC value of IE. Also, you will notice that you can get relations between these three parameters. So, for example, because you have in the active region, you have a relation between IC and I base, a relation beta, so you can replace IC by beta I base. So you will find that this can be written as beta, for example, divided over R pi. GM can be written as beta divided by R pi. Okay, so you can find the relation between GM and R pi. You can say that GM equals beta divided over R pi. Also, you can replace IC by alpha IE, so you can say, okay, it's alpha over RE. So you can find the relations between GM, R pi, RE, because we have already relations between IC and I base and IC and IE. Okay, so this is how you calculate the parameters. The parameters, in order to calculate the parameters, you have to solve the DC circuit first. You have to calculate the DC value of IC, collector current, the base current, the emitter current, and then you substitute in these equations in order to get the parameters that you are going to use in the AC analysis. So you cannot solve the AC analysis before you solve the DC analysis first. You have to solve the DC analysis first, calculate the DC values of the currents, and then use the DC values of the currents to calculate the parameters that you are going to use in the AC analysis, in the AC model. Okay? So first step will be to solve the DC analysis, then you solve the AC model. Another relation that you can find also between R pi and RE is R pi equals 1 plus beta RE. So you can find also another relation. I'm going to remove this. You will find another relation between R pi equals 1 plus beta RE. And this is an intuitive thing here, that a resistance that exists in the emitter, you can move it to the base. But because when you move it to the base, it will see lower current. The current of the base is lower by a factor 1 plus beta. You have to increase its value by 1 plus beta so that the total voltage remains the same. So here, in these two models, either you put a resistance here, R pi. In this case, R pi, it has a current I base. So the voltage, it will be I base R pi. Or you put the resistance RE in the emitter. And in this case, it has a voltage IE RE. And because IE is higher than I base by a factor 1 plus beta, IE equals 1 plus beta I base in the active region, right? Then Because IE is higher, RE must be lower. Or in other words, R pi must be higher than RE by a factor 1 plus beta. So because IE is higher than IB, then R pi must be higher than RE by a factor 1 plus beta. R pi equals 1 plus beta RE. This is because IE equals 1 plus beta I base, so that when you multiply, you will get the same voltage exactly. Okay? And this is something that you will see later, that if you have a resistance in the emitter, you can refer it to the base after multiplying it by 1 plus beta. Okay, so this is how to calculate the parameters, the different parameters in the AC models. And as we see, again, in order to calculate the different parameters that you are going to use in the AC analysis, in the AC models, you have to solve the DC first in order to calculate these parameters. Last thing before we finish is, so far we didn't include early effect in these models. But we know from early effect that the current of the collector, practically speaking, it's not just a constant beta multiplied by I base. This is not a constant. Usually to represent early effect, we include a factor here, which is, let's write it in another color, we include a factor 1 plus VCE divided over the early voltage, right? So we said that this is the practical equation of IC that includes the early effect. This is a constant I base, this is without early effect. If you want to include early effect, you have to multiply by this bracket, 1 plus VCE over VA. This means that IC also depends on VCE, right? It doesn't depend only on VEB or VBE or I base. It doesn't depend only on VBE or on I base. It depends also on VCE. So there is a relation between IC and VCE, which means that if you change VCE a little bit, if VCE is changing a little bit, IC also will change. How to include the dependence of the collector current on VCE in these models? As you see from the current models, IC, it's dependent only on VBE or on I base, beta I base. It doesn't depend on VCE by any means. So how to include the early effect, how to include the dependence of IC on VCE? Again, if we notice the relation between IC and VCE here, we notice that it is kind of a linear relation, right? And the linear relation between IC and VCE can be represented because they are in the same side of the circuit. IC and VCE, they are in the same side, and they have a linear relation between them. This can be represented by a resistor. So we can represent the effect, early effect in our circuit, the linear relation between IC and VCE in our circuit by adding a resistor. This is VCE, this is IC. So we can come here and add a resistor. We'll call it RO. This resistor will model the relation between the current IC. Of course, the current IC will be the current here, the total current here, okay? And this is the total VCE, okay? So the current here will consist of two components. One of them is dependent on VBE, and the other one will model the dependence of IC on the voltage VCE, okay? Of course, we are talking in the models. We are talking about AC components only, so should be all small letters, all small letters. So here, the current of the collector, it has two components. The AC component of the current of the collector, it has two components. One component dependent on VBE, and the other one dependent on VCE, and the total current of the collector will be the summation. Same thing here. In order to include the effect, the early effect, here in the T model, you have to add a resistance between the collector and the emitter. So between the collector and the emitter, let's put it here, okay? IC will be this total current, and between the collector and the emitter, you have to add a resistance like this, okay? okay, to model the dependence of IC on the voltage VCE. So the voltage VCE is between these two terminals, between the collector and the emitter. The emitter is here, by the way, and this is the current of the emitter. Now the total current, and this is the current of the collector. Okay, there are two components for the current of the collector. One of them is dependent on VBE, and the other one will be dependent on, VCE. Okay. How to calculate the resistance that models the linear relation between VCE and IC? Again, you have to calculate the slope between IC and VCE, and then you take the inverse. So if you calculate the slope between IC and VCE, if you take the differentiation, in this relation, and then you take the inverse of the slope, you are going to calculate RO. So RO is basically 1 over the slope at the Q point. 1 over the slope, in which curve? Slope of each curve? The slope of the relation between IC and VCE at the Q point. Okay? So, basically, it's dIC by dVCE at the Q point. This is the slope, and then you take the inverse. So basically, you need to differentiate this relation with respect to VCE, which will be beta I base, and when you differentiate this, you will get 1 over VA, right? And then you reverse the relation. When you reverse the relation, you will get, this is inverse, this will give you VA over beta I base at the Q point. And at the Q point, VA will be VA over beta with the DC value of I base, which is approximately VA over, what is beta I base? Approximately it's IC. Force here when we say approximately because here we neglect the early effect. We neglect the early effect. We say that IC equals beta I base without the early effect. That's why we say approximately. And the difference will not be much because the early effect is very minimal compared to beta I base. Okay? So here the RO can be calculated as VA, the early voltage, the magnitude of early voltage divided over the collector current, the DC component of the collector current. So when you substitute here with the Q point, I base, the total I base at the Q point is the DC value of I base. Beta multiplied by the DC value of I base is approximately the DC value of the collector current, and from here we can calculate, or we can say that RO equals, since it's a resistance, by the way, all the resistors you will find that they are voltage over current. The conductance, it's a current over voltage. And for all these, we use VT. For the early voltage, because it depends not on VT, it depends on VA, it will be VA, voltage VA over the current of the collector. Again, to make it easy, resistors are voltages over current. Conductance, current over voltage. Always the voltage VT, except for the early effect, the voltage is VA. When you calculate R pi, this is the resistance connected to the base current. So you divide VT over the base current. RE is the resistance of the emitter. You divide VT over the emitter current. RO is related to the collector and early voltage. So it's early voltage over the collector current. GM appears in the collector also. So you expect that it will have a collector current divided by VT. So this is just to make it easy for you. So R pi is related to the base current. You expect that the base current will appear here. VT over the base current. RE, emitter, so VT over the emitter current. GM related to the collector and it's a conductance, so it will be collector current over VT. RO is related to the collector and the early voltage, so it's early voltage over the collector current. So these are the different parameters and how to modify our models in order to include early effect. So if I tell you that we have early effect in the problem, you have to use one of these two models. You have to include RO. If I didn't mention anything about early effect, then you remove this RO and use the simple models. And that's it for the pi and t models. That's it for the pi and t models. And we'll see you in the next video with the different amplifier families and examples on the different amplifier families.